Okay. Last time we learned about logistic regression, right? So here, and this sign seems strange. Just and yeah. Anyways, this is the sigmoid function. Okay, so we are inputting this linear layers output to this sigmoid, and that's the logistic regressor. So sigmoid is output is bounded to 0 to 1. So we want to threshold our output somehow using this type of medium value. And if the value is larger than 0.5, we will classify that sample as positive class. And if the value is less than 0.5, we will classify that as minus class. Okay, so logistic regression, we want to achieve the binary classification. Okay, the classification which has only two labels. And for that, uh, we are using this type of binary cross entropy laws. Okay. Okay. This is the binary cross entropy laws we have learned. Okay. And in the PyTorch code, we can just specify that as the BCE laws, which is the abbreviation for binary cross entropy. Previously, we usually use MSE laws, okay, which was the mean square error laws. And this is for normally this is for used for the regression task. But here we can just change this loss function towards the BCE loss. And anyways, this will work for this binary classification task. And for extending our network to role as the multi-class classifier, we have to type of softmax operation in the last layer. Okay. So the last layer's output have to be non-negative, and also their error sum should be one. Okay. If this if each element denote the probability, then their value have to be non-negative, and also their sum have to be one. Okay. So to meet the condition, we are applying exponential value to each entry, okay? And then we are normalizing each element by their error sum, okay? So that's the softmax operation, okay? And also these softmax, they are differentiable, their output is differentiable respect to their input, and there is no parameter. So this could be used in the deep architecture, okay? And also, we need cross entropy laws to train the multi-class classification task. And you can, by just simply extending the binary cross entropy to the multi-class case, you can understand this. Okay. So this is the cross entropy laws, and this is our prediction, and this is the ground truth, which is one hot encoded vector like this, having just one and having zero for remaining entries. And P, this is the constant because ground truth will not be changed during the training. And Q, that is the variable. And you can, you can to say further induce the formula as this, then this entire term goes to constant, and the formula becomes like this. And this is the famous term called as KL divergence that measures between two probability. So this becomes minimum, this term becomes minimum when this is equal. So by minimizing this KL divergence, I mean, minimizing this loss function is equivalent to minimizing the KL divergence between P and Q distribution. And by minimizing that, you can secure this Q becomes close to P. And that is actually what we want, okay? So using this cross-entropy loss, we can train our multi-class classification network. Okay. And the loss function, for the loss function, you can use this cross-entropy loss. Okay. By changing the loss function as cross-entropy loss from BCE or MSE, you can train the multi-class classification task. Okay. But one thing you have to remember is, I mean, in the MSC laws, um, the right side is the ground truth. For these cross-entropy laws, the right argument, that is the ground truth. And the left argument, we have to input our predicted value, okay? I mean, in MSC laws, their dimension is same, okay? In MSC laws, we are directly making this predicted value goes to this ground truth value, okay? So their dimensions are usually same, but in cross-entropy laws, you don't have to be confused about this. So, I mean, PyTorch, they are providing, making this easy. They intended to make this process easy. So here, I mean, for example, if you print out your input, that seems like this. So there are three samples prediction having 5 classes. So, but we are not using softmax yet. So these values are having some random positive and negative value, and they are not, their L2 Aaron summation is not 1, okay? Because I just want to make some random input here, okay? Whose dimension is 3 by 5, okay? I just want to check for the dimensions for these laws. So this value, you can regard this as one sample's prediction for 5 classes, okay? So there are actually 3 samples prediction for 5 classes, and your target have to be, uh, I mean, not 3 by 5 dimensional value, but having just 3 integer values, okay? Because you are doing the classification out of 5 classes, you have to choose the one ground truth value. So here you are defining your ground truth class as 2 for first sample, and you are specifying that the second sample will have the class 1, okay? And the third sample will have the class 0. So by specifying this 2, 1, 0, you are saying that the first sample is classes 2, okay? The second sample that's what to say, ground truth label is 1, and for the third sample is ground truth label is 0, okay? And then you calculate this loss value, and if you print out that, you can get the cross entropy value that is applied to this input and target values. Okay, so this is the value calculating the cross entropy for these 2 metrics. Okay, are you guys following this? Okay, so I mean, when applying MSC laws, usually input and target, their dimensions are same, but PyTorch is making this use of cross entropy laws easier, but sometimes this makes confusion. So don't confuse this. Okay, your ground truth is some integer values for number of samples, and your predicted values, that's the dimension of number of samples multiplied by number of how to say classes, overall classes. That's your predicted value. Okay, so in the code, don't confuse this. Okay, I mean, if you sometimes confuse this, and if you make your target value as really like this type of one hot encoded value, okay? So I mean, because I said to you the ground truths are one hot encoded value, so you indeed can make this type of one hot encoded ground truth for 3 samples. Okay, if this task is having 5 classes, and if there are 3 samples, you can represent uh, this as the ground truth as well. But this does not work in the code. Okay, so do it like this. Okay, and then we will learn about the LUNET architecture and uh, as as far as remember, this is anyways the early 1980s. Okay, so I will check about this. Okay. Anyways, this architecture has been proposed old. I mean like 30 or 40 years ago. Okay, for doing actually the classification for this data set, MNIST data set. Okay. If you take AIP2, maybe you already did some experiment doing this, okay? But at that time, you don't understand the details, but now we will learn more details about that, okay? So we will involve the CNN architecture, okay? And the input size is quite small, 32 by 32, and they are gray images. Okay, so 32 by 32 by 1 dimensional images are inputted, and at the end, you want to estimate 10 dimensional vector, which denote the probability for 10 digits. Okay, so even though here the figures are having alphabet, but we want to classify digits. Okay, so this is the CNN architecture, which is similar to what we have learned, but I will detail that. Okay, so this is some, we have to import some packages, okay, mostly PyTorch and their libraries. And this is for plotting graphs. And we also have to import some NumPy package. And also this learning rate as the epsilon in gradient descent formula, okay? And batch size, which means the uh, image processing unit. So, I mean, we will simultaneously process 32 images together, okay? We are doing this because it's faster, okay? Uh, so we will process, I mean, we hold that as the batch processing, which means we will process multiple images together, okay? That's faster, okay? And we will, train our network using 100 iterations, okay? And our image, their size is 32 by 32. We have to specify it here. And we want to classify it into 10 classes, okay? So here we have to define some hyperparameters, okay? And this is the LUNET architecture we want to use, okay? So this is the similar code we have learned when, defining the CNNs, we have to define the class in the Python, okay? And this is the constructor which will be called once when the instance is created. And there are two parts, the feature extractor, which is composed of mainly the 2D convolution operation. But for the classifier, we will involve it using the MLP layers, linear layers, okay? And you can see here, they are using tangent hyperbolic functions instead of the ReLU function, okay? At that time, there was not much knowledge on these nonlinear functions, okay? So, but here, I mean, as I told you, tangent hyperbolic, it has some problem, some issues when x values are becoming larger or becoming smaller. Their gradient is becoming to zero. Okay, that's unwanted things. So we are later replacing this with ReLU functions. Okay, in practice, it works better than this tangent hyperbolic. So we are using this. Okay, because of that. And as I told you, this is the forward function. So feature extractor is first applied, and then we are flattening the signal to the one-dimensional signal, and then we will further apply the linear layers, okay? And this represent this architecture, okay? And we will further check if the dimension is correct, okay? So previously I mentioned this to you. Okay, this is the formula that can calculate the output size of the convolution operation from the input image size. Okay, so as I told you, the input image now is 32 by 32. Okay, so I is 32 for the I mean the input is 32 by 32 by 1 here. Okay, so it means this layer first. Okay, this layer is first inputted. So it input one channel signal and it will output six-dimensional output. Okay, and because this is the convolution operation, their output size, their 2D output size will meet this condition. So their input is 32 and there is no padding. And the corner size, there's no padding because you didn't specify any padding related argument here, okay? And corner size is 5, okay? And stride is 1. So here it would be 28, okay? Right, there's a plus 1 here, right? So after this layer, you will get this dimensional array, okay? 28 by 28 by 6, okay? And actually, that is denoted here in this figure, right? When implementing this CNN, when designing these hyperparameters for convolutional layers, you have to carefully design this, okay? Also, this is required when you're fulfilling your assignment, okay? And then it is these nonlinear layers will be applied and their dimensions are same. But if you apply this average pooling with corner size 2 and stride 2, that will reduce your output like this, okay? I mean, 2D dimensions will be reduced 2 times, okay? It will be halved after this pooling operator, okay? Because it's corner size 2 and stride 2. So it is exactly the pooling operation we saw here. We saw, we saw this type of pooling, okay? The stride is 2 and window size is also 2. So it makes the input size halved. And then here, you define another convolutional layer and input size is 6 and output size, channel size would be 16. And kernel size is, filter kernel is 5 and stride is 1. So you will also calculate, and padding is 0 again. So your output from this convolution operation will be 10. Okay, here you will get 10 by 10 by 16 dimensional output. Okay, and you will apply tangent hyperbolic and it retains the dimension. And if you apply the average pooling, then the signal will be reduced again to 5 by 5 by 16. Okay, and if you apply this another convolution operation, defining its input channel as 16 and output channel as 120 and kernel size 5 and stride 1, then you have to calculate again this. Then your final output would be 1 by 1 by 120 here. Okay. Are you guys following this? And then we will apply tangent hyperbolic. And this signal is now 1 by 1 by 120 dimensional array. Okay. And you will flatten it, okay, to make it just the this dimensional 1D vector, okay, right? And then you will now assign it to linear layer, which is just applying this type of operation, okay? Input feature dimension, that's 120, and output feature dimension, that is 84. Then after this, you will get this dimensional one-dimensional vector, okay? And then nonlinearity is applied, and then this layer is final layer. So this dimensional vector is mapped to n-class dimensional vector, and n-classes is defined here as 10, okay? So this is 10, okay? So your final output here will be 10-dimensional vector, okay? Are you guys understanding this? So this, this LUNET architecture, if you draw that in here, then you can see this dimension, you can calculate, okay? Seeing the convolution and their hyperparameters, okay? Okay, so and then now we define our architecture here, right? And then the next thing we have to do is we have to load the MNIST dataset. Okay, here MNIST dataset, their image size is 32 by 32, and it has 10 classes which represent digit. Okay, so for this image, the class is 3, and for this, its class is 0, like that. Okay? But thing is, this type of famous data sets, okay, this is the MNIST data, and actually I changed this URL. So, maybe if you print out your material or you are seeing the material uploaded in the web page, I didn't update it yet, so the URL may be slightly different from this. It is updated. If you follow this anyways, I will update it later, okay? And anyways, if you follow this, you can see the list of famous data sets like MNIST. In the PyTorch, they are already implemented the data loader for these famous data sets, okay? So, for example, the thing you have to do for MNIST dataset to load that is just calling this dataset.mnist. Okay, the dataset package you are imported from here, right? And you can just access this dataset.mnist, okay, by importing the dataset. Okay. Um, Anyways, two things you have to do to load the data in the PyTorch is you first have to define uh, this type of data sets, okay? And then you have to input it to the data loader, okay? Data set, that is the instance that can understand uh, how to say, how to load one sampled data from the this repository. Okay, so this train underbar, sorry. So uh, this train underbar data set, they have to know how to load the X and Y this pair for one sample. Okay, that have to be defined from this datasets class. But in data loader, using this information, so here you are inputting this train underbar dataset, okay, into which dataset you will use for this data loader. And this data loader is providing you easy interface to load the data, okay? So as I told you, we will process multiple images, okay, together, and that is called as batch. And you can specify how many images simultaneously process here. So batch size, we defined it as 32. So we will use 32, we will simultaneously process 32 images together, okay? And this shuffle means you will shuffle the orders of the data, okay, from the when loading the data. And also you can use another argument, okay? This data loader is having many arguments that can provide you easy interface. Okay, for example, you can parallelize using threading this data loading to accelerate your training code. Okay? And that kind of options are contained in this data loader. So this data loader is providing you, this is implemented by PyTorch and helping you to efficiently read data, okay, for these specific data sets. And before using this data loader, you have to specify how to read your okay? Okay. That have to be defined in dataset. And for famous datasets like MNIST, the PyTorch is already defining it. Okay. So in this, for example, in this MNIST, you will get that MNIST data. And even if you didn't download that MNIST before running this code, if you check this as true, this flag download as true, the code will automatically download this MNIST dataset, okay? And locate that dataset in this folder and will automatically start the training and testing. And also you will specify which kind of transformation you will automatically apply for every training data here. So this type of trans means transformation, and you will apply the resizing operation first, okay? This resizing operation first. So this is the grammar in the PyTorch as well. And also we are wanting to transform their types to the PyTorch tensor. Okay, so we are loading the training image and wanting to resize its size to 32 by 32 and wanting to change that as the PyTorch variable. Okay. And whenever we load the training data, we are applying this transformation for, having the resizing and typecasting to the PyTorch variable. And if you don't have that data set already, you will download that, okay? So this is the data set provided by the PyTorch, okay? But thing is, you sometimes want to use your own data for training and testing. And in that case, you have to define your own data set. For the famous data set like MNIST or other ImageNet or CIFAR, others, they are already contained in the PyTorch. But if you want to collect your own training data or own testing data, and wanting to use that in the PyTorch, then you have to define your own data set class, okay? And I will show you the examples for this dataset class, okay? The thing you have to define is these three methods. For the constructor, you have to specify where your X and Y data are located, or the value itself, okay? So here, they are containing all the X and Y data in this init function, okay? So this is the first class's X value, the raw data, and their class, their ground truth Y, okay? They are directly contained in this constructor. But if your data is too large, you cannot do this kind of thing, okay? So normally we specify the image path, okay, or other types of data-related information we initialize in this constructor. And this length, this is denoting how many data you will use, okay? So here we can just return the length of X data, okay? And this get item is important, okay? This get item defines in which format you will read the data, okay? So if you input index, then you will get one sample for this index K array, and you will typecast it to PyTorch tensor, and then you will return that X and Y here, okay? So this data set is defining how your X and Y data for one sample is returned, okay? And then you can input the instance in this data loader class, okay? And you can define how, you can, extend your batch-wise processing, or also you can define you will use parallel processing for data loading or not. And also this shuffling is required only for the training samples, but for the testing, you are not normally requiring this shuffling. So this is quite natural things, because in the training stage, if you see training samples in fixed ordered form, okay? In the training data, if there are 1,000 training data, and if let's assume that you are seeing that 1,000 samples in fixed order always for every epoch, that will somehow make your network tuned overly tuned for those orders of the data. Okay, so to prevent that, we normally do shuffling on the orders of the. Let's say there are 1,000 data, and if your network is seeing that same data, even for the same data, if your network see those data in different order, then that can help the training data, training process. Okay. But at the testing, uh, this shuffling is not that helpful. If you, even though you do shuffling for the testing stage, the accuracy will be safe. I mean, let's assume that when you learn about this, how to say, let's assume this network training. Uh, I mean, this is similar to teaching the babies, right? So let's assume the network is baby, human baby, and training during the training, if we teach the baby to do something in fixed order set of the data, then the baby will be bored, okay, and easily tuned to the training data. So the training becomes not that efficient, okay. But if you change the orders of the training data, then it can help training process. It can improve the training process. So you can understand that in that way. But after training, the baby already knows some concept. Okay. Then you want to test your current model. Okay. For the some other testing sample. Uh, I mean, if even though you shuffle the data, test sample, let's say there are 100 test sample, and if you do testing for that 100 sample, and uh, that model is producing like 80% accuracy, but even though you shuffle the test data and show that to the same model, then accuracy will be safe. Okay? Because there's no further learning, okay, here. So even though you, you can use the shuffling here, but that does not do anything, okay? So that's why we do not use shuffling for the testing data. Anyways, if you use this PyTorch built-in data loader, managing the data, it becomes efficient. Okay, so that's why we are defining the data set first, which defines how to return XY pair for one sample. And using this data loader, you can make it parallelized. Okay, so this is the data loader. And also, if you actually, this is very important thing. If you define your data set class as this, and you define get item method like this to return this xy, then in the for loop, you can make your train loader, okay, and you can directly, how to say, use this data loader inside the Python loop, okay. Then for each for loop, you will get new X and Y samples from this data loader. Okay, so this is another benefit. If you use this PyTorch built data loader, then you can, how to say, uh, use this kind of features for loading the data. So this is very easy to use, right? So I recommend to use this data loader when implementing the PyTorch code. Okay. And another thing you have to understand is stochastic gradient descent. Okay. So we have so far learned about the gradient descent, okay? And this is actually very important concept. So, but easy, okay? Very important, but easy. We have learned about the gradient descent formula, okay? Like this, okay? Uh, Gradient descent and stochastic gradient descent, their formula is same, okay? But there are, difference lies in how to load the data, okay? So this figure is well explaining the difference between these two. So far, we did gradient descent, okay? So after seeing all the training data, we calculate these ones, okay, to update the parameters, okay. That's the gradient descent. But stochastic gradient descent, we will see only the partial data, only the subset of entire training data, and then using this mini batch responses, we will apply this parameter update. Okay. So in stochastic gradient, there will be multiple parameter update after seeing the partial data. Okay. Are you guys understanding this? But in gradient descent, you only calculate this once after seeing all the training data. Okay. That's the difference between these two. Okay. So calculate for all data for this gradient and then go one optimal step. Okay. One thing you have to remember is this DL dissector is also accumulated through multiple data. And then this is one time calculated, okay, in gradient descent. But stochastic gradient descent, you will calculate gradient for for example, 32 images, like, out of 1,000 total training data. So you will see only the partial data and calculate this and update this for that partial data. So this is only difference between stochastic gradient descent and gradient descent, okay? But if your data is large, this is quite inefficient, okay? I mean, if you, let's say you have 1 million data, then seeing 1 million data may take like one to 2 hours, okay? And if you train your model for 1 day, your update will happen only like 20 times, okay, right? So seeing this will take like one or 2 hours. And if you train this network using this amount of data, there will be only 20 times parameter update, okay? But if you use this stochastic gradient, depending on which batch size you will use, there will be multiple, parameter update happen, right? And in practice, this works well. Okay, if your data is large, in practice we observe that this stochastic gradient descent works well. That's the conclusion. But if you think it logically, gradient descent that calculates the optimal gradient for by seeing entire 1 million data. Okay, and then it goes one optimal step. Okay, even though it goes 20 update, but that 20 steps will be optimal. Okay, right? So this figure is showing that. So this is the parameter space. Okay. This is the set, Okay, and W, but you can use it double sector here. The black line is meaning the gradient descent. Okay, it will go to the what are few optimal steps. Okay, and after that few optimal steps, it will converge. Okay, but stochastic gradient descent, it will move multiple non-optimal steps because it shows only the partial data feedbacks, right? So one step might not be optimal, okay? So there are many noises here, okay? There are many noises here. But in practice, stochastic gradient descent works better than gradient descent. I will explain that why. So stochastic gradient descent, it calculates gradient for partial data, and of course, it takes small amount of time, okay? And go many non-globally optimal steps, but it converges, okay? I mean, the reason why this stochastic gradient works better than gradient descent is we are training using train data, okay? In training, during the training stage, we will train the sector of this network parameter to converge it and apply this gradient descent using the training data. Okay? But at testing, we are testing using the test data and training data and test data, they are different. Okay? So gradient descent, they are optimal with respect to the training data. Okay? We are getting the model which is best fitted to the training data, but it is not always best for the testing data. Okay? Even though we get the best model for this training data, it would not be best for unseen testing data. Is that correct? This is important, actually. 이거 이해됩니까? 이해 안 되는 사람? 네. 다 이해되나요? 아니, 헷갈릴 수 있는데. Anyways, we are training our model using training data, and we eventually we are wanting to get good accuracy for testing data. Okay? But even though we achieve the best fitting to the training data, it is not guaranteed to get good accuracy for the testing data. Okay. So because of that, gradient descent is going for the optimal step, okay? But it is optimal in the with respect to this training data, okay? Not guaranteed to the testing data, okay? Stochastic gradient descent, it goes to non-optimal steps, but it is non-optimal with respect to training data, okay? It has some noisy, but this kind of noisy sometimes helpful for, I mean, getting good accuracy for this type of unseen testing data. Okay, are you guys understanding this? So because of that, in practice, stochastic gradient descent, that works better. That works better. Okay, than the gradient descent. Okay. Go one optimal step, but that optimal is different from what we want. Okay. Okay, that's important difference between this stochastic gradient descent and gradient descent. So I will show you the example of gradient descent here. Okay. Oh, sorry. Here, this code is actually, even though, this function is called as stochastic, this function is defining stochastic gradient descent, okay? Uh, we can reuse this SGD for GD as well because their formula is actually same. But actually this code is defining the GD instead of SGD because for each epoch, we see all the X and Y, okay, already contained in the array, okay? And then optimize your model after seeing all the X and Y, okay? Here in this code, you are implementing the gradient descent, okay? Because your X and Y is small enough to be contained in your array, okay? In the one variable, uh, we can apply gradient descent here, okay? But in practice, if your X and Y, their pairs are too many, then you cannot store all the data inside one variable, okay? And actually, you cannot use the gradient descent for large-scale data. And also in practice, so that because of that, you are, motivated to use this stochastic gradient descent, seeing only the mini batch. And in practice as well, this mini batch update, that works better than the gradient descent. So, that is very good thing for us, okay? And actually, this implementation is the real SGD implementation. Okay, as I told you, we will define the data loader for the training samples. Okay, and this train method will define how you will train your network used for all training samples. Okay, so one epoch training. One epoch means one time seeing all the training data. That is one epoch. Epoch means seeing your old data. Okay? So this train method will define one epoch training, and it will input your model and train data loader for the training data, and your loss function and your optimizer. Okay? And this is for initialized for visualization purpose. And you also have to always do this. Your model have to be in train mode. Okay, you have to remember not missing this one line of code whenever you train your model. In when they are in the testing phase, you also have to change that into that evaluation mode. Okay, so don't forget you turn your model into training phase, okay, before doing the training. And from the data loader, you will get your X and Y data, okay? So here, X and Y, that will be in the batch size. So our batch was 32 images, okay? Here, X and Y, you will get 32 samples X and Y, okay? And then you will apply this, you will set your gradient into 0, and you will calculate your forward process, okay? You will apply model to your input, and this is the output, and calculate the loss function, okay, on that, okay? And this is applied for visualization purpose, okay? And anyways, this is for visualization, mostly for the visualization purpose. And important thing is here, after calculating your loss, you will call this loss backward to calculate DLD sector, and will optimize the sector by calling this optimizer dot step. Okay. So anyways, you have to remember that this code are updated for mini batch. Okay. So this is actually the code implementing SGD. Okay. But if your X and Y are not coming from data loader, but having all the training and testing data, then that will be GD. Okay. That's the difference. Okay. But I mean, implementing GD for large scale data, that is also impossible, okay, actually. SGD is practical, actually, and also guarantees good, better accuracy than GD. So that's why we are using GD. And for here, I mean, uh, so here, for the predicted Y value, uh, argmax, this is actually finding the maximum entry. Okay. For this probability vector, you will get the maximum element and their index actually. So this is actually the class we are, how to say, we are inferring. Okay. So y hat, this is the probability vector we are outputting. And by applying this argmax, we are getting the maximum index. Okay. That is actually the class prediction. Okay. Are you guys following this? Okay. And we can, if that class information is same as the ground truth y, then we can regard it as the correctly classified sample. So we are calculating the accuracy here. Okay, so this is actually for the visualization purpose, but important code is here. Okay, and this is also visualizing their accuracy and loss. Okay, in the middle. And for the testing code, this is testing for one epoch, okay? One entire testing data. You want to do testing, and your model have to be in evaluation mode, and this have to be initialized, okay? The important difference between this testing and training is the previous training code is here there is no 이걸 보려고 하는데. Okay, anyways, there's no this code. Okay. So here previously there was load stop backward and optimizer step in this part. But at the testing, you only do forward pass, okay, and calculate the loss and the classification accuracy here. So here, the difference between testing and training code is the existence of this code or not, okay? And also this part is also not necessary for the testing data. So these two codes are not in the testing part, okay? But remaining things are same, okay? And also you have to make your model in the evaluation mode, okay? That's the only difference in the testing code. And in the training loop, okay, using your, to say, training and test data you defined in the previous slide, okay, in this training loop, you will implement train for 100 epochs, okay? So, I mean, already mentioned that the training and train test method, they are implemented for one epoch training, okay? And so they are called in this part, okay? So you will use another for loop here, defining 100 epochs, and you first learn the train code we define and apply test code afterwards. And then we visualize the training information, okay? And another thing you have to see is this code is used for test branch. Okay. So for the test branch, you will not requiring any gradient calculation, right? So I mean, for the code that is not requiring this gradient calculation, you do not need any graph construction as well, right? So uh, this flag is making your code execute faster than the training mode, okay? So that's the purpose of this code, okay? You do not, if you do not specify this, functionally it works same, but slightly slower, okay? Anyways, this is the code for implementing the training for 100 epochs. Okay, so after training for one epoch, so this is the returned model. Okay, so before uh, I mean this model was the having the sector old. Okay, and this model is having sector new. Are you guys understanding this? Okay. And then you want to test the accuracy on the testing data using the new model having sector new. Okay. And they are visualizing your training loss, testing loss, and accuracies. Okay. Are you guys understanding this? Okay. And this is the top module. Okay. So at the top, you have to define your model using the model we saw here, okay? So using this class, we are making the LUNET architecture here, okay? And defining the optimizer using SGD, okay? And using the cross entropy loss, we will train our network because our task is classification task. And using this training on the bar loop that train our model for 100 epoch, we want to train this model. Okay. Are you guys understanding this code? Okay. Using this type of code from here to here, we can train the CNN network. Okay. And this is the output. Okay, actually. So we are visualizing for each epoch, seeing one entire training data. We are visualizing our training loss, testing loss, accuracy. Okay? And you can see our loss is gradually reduced and accuracy is gradually increasing. Okay? But one thing is it takes some time, even though MNIST dataset, their data scale is small, it takes a few minutes for small epochs. Okay? It is slow. So if you use only the CPU, that is slow. Okay, so we have to use GPUs. Okay, when doing this deep learning, and that can accelerate the training process. Okay, I mean CNN that is composed of multiple simple units. Okay, so using GPUs, we can efficiently accelerate each operations, okay, easily. So in the collab, when importing this PyTorch package, and this flag is actually showing that your environment is having GPU or not. Okay, so if this is false, then you cannot use GPU. Okay, I mean in your desktop, if this flag is uh, false, even though you have GPUs, then you have to install some CUDA related library properly. Okay, then after that you can see these true flags. But in the collab, the thing you have to do is following this menu, and you have to select the GPUs and click the save. Okay. Then after doing this, you can see a true flag for this variable. Okay. Then if this flag is true, then you can now ready to use the GPUs. Okay. And then in your code, you have to fix your code to use the GPUs. Basically, what you have to do is copying your data into the GPU, and also you have to copy your model in the GPUs. Okay. So for that purpose, you have to extend the argument for this train method, and you have to copy these x and y variables. Okay. And this device is defined later, and this device is meaning CPU or GPU. And also for the testing code, you also have to extend one argument, and you have to copy all x and y data to the GPUs before using. And you have to transmit this device from the top module to the sub method. Okay. And at the top, you are defining this device. Okay. So when this flag is true, you will define this device as CUDA, which means GPU mode. Okay. Else, if this flag is false, then you will use only the CPU mode. Okay. And then you also have to copy your model to the GPU. Okay. And you are transmitting this device to sub module, and in that sub module, as we see, they are copying XY data to the GPU. Okay. So you have to do this, and their functionality is same, but it's becoming faster. Okay. So this is the way to use the GPUs. And next class, this Wednesday, we will learn about more famous architectures like AlexNet, VGGNet, GoogleNet, ResNet. And actually, they are the state of the art that achieves the good performance for ImageNet challenges. Okay, so they are sharing very similar architecture to LUNet, but having some of innovations. So we will learn about that. Okay. Okay, see you Wednesday. Thank you.